Okay, great. All right, why don't we get started? If you have something to share, please share. It's hard with 41 people in the class if everyone's having side conversations. Um, any questions so far about the material? No questions? No? Hopefully keeping up. The whole semester's mapped out. All right. So today, the goal is to minimize the time that we spend finishing up the material on search, and I want to spend the bulk of today on walking through the code in support of project number two. There are some gotchas in the code that aren't really documented anywhere. So to save you all the trouble, I wanted to go through some of that. Um, but before we begin, the usual administrative bits. The reading certainly has not changed. The reading is completely mapped out in the syllabus for the entire semester. The book is actually very good, so please make sure you're keeping up with the reading and engaging with the material. Project number two has been posted. You should see it on Canvas and also on Gradescope. When you click through the submission on Canvas, it'll bring you to Gradescope. It is due the 3rd of February. So it's about a week and a half or so from now. The first three questions after today, you'll have enough to complete those. So please make sure you pay attention to the fact that you're given a week and a half instead of just a week, because it'll take you longer to do some of these. And moreover, the material we're going to start on Tuesday is going to be relevant to completing some of the other questions in project number two. Okay? All right. Any questions? No? All right. And so when you see recommendations on project number two, don't edit this, don't do that. That's really, really important because there are very many opportunities, excuse me, to break the auto grader, right? So it's really, really important to do that. One thing that I will note or highlight for the submission instructions, I only have a single instruction, right? And that's to put the code that you edit, those Python files, in a zip and then upload it. It does work if you upload the files individually, yes, but there are opportunities for, oops, I forgot something, right? So I always specify just one method because I can't have, 5 or 6 different ways people are doing things across 41 people in the class, okay? All right. So why don't we jump right in? And so the usual, I'll start out, warm things up with dad jokes, right? I have lots and lots of them and some secret scrolls I keep locked up in a safe at home. But my father, he didn't watch movies. He wasn't a movie guy. But there was one thing he would go to the theater when he was alive and he would watch, and that's 007 movies. And so I don't know if you have a favorite 007, this character who works for the British clandestine service as a spy. And when I was a kid, I wanted to be a spy. And I remember getting an electronics kit and learning how to send on AM radio broadcasts. So I built a listening device and I planted it in the house. And I was in my room tuning the radio to AM channel to get whatever someone was saying. And then there was a knock on my door, and it was my mother. And needless to say, my burgeoning ideas about a spy career ended that day, right? It was many years ago. So I could have been a spy looking up your information rather than a professor teaching you AI today. But nonetheless, everyone has a favorite Bond. Do people watch 007 movies? No? Are you familiar with 007? Okay, just one or two, a couple. All right. And so Daniel Craig is the current Agent 007, and Sir Sean Connery, I think, is the best Agent 007. Sean Connery is Scottish by origin, and he was knighted by the Queen of England. And so I found the intro music. I love this. Okay, so what does that have to do with search? Not really anything. It's a dad joke. But the question I have for you to warm things up, where did Agent 007, after he retired, where did he invest his retirement? What do you think? And this was not in the slides. Bonds, yes, the bond market. And I saved this one. All right, that was the one that wouldn't play. Nonetheless, the bond market. Okay, very funny. Haha, I think it was funny. Thank you, Alexander. Oh, all right, so where we last left off, that would have been great for depth first search, right? Where we last left off, we talked about depth first search and the goal or strategy of node selection for DFS, depth first search. I can never say depth first quickly. Um, for DFS is to expand the so-called deepest node first. And if you implemented best first search, which we described last meeting, you could treat depth first search as a special case of um, of best first search of BFS. I'll just abbreviate because I can't say the B's and the D's too quickly, but it's a special case of best first search where your performance evaluation is the negation of the depth of the node. And so DFS is a tree structured search, and it doesn't keep or doesn't need to keep a table of reach states. It always pursues the deepest node until it exhausts the successors, reaches the bottom or the leaves of the tree, and then it backs up and then takes the next available pathway, looking again for the deepest node. And so we'll continue on with depth first search. And where we left off, we had this illustration. And this is in the book, figure 3.11. And you read this left to right, top to bottom. So we start with node A as the node we're going to expand. And we generate its successors, reaching nodes B and C, our frontier. And then we select that first node B, that first child, and we generate its successors. And we encounter nodes D and E. And then we select that first node D. We generate its successors. So we encounter H and I. And then we notice that H doesn't have any successors. And on the next round, we back up and we expand I. I does not have successors. So we back up to D, back up to B, go down to E, and we expand its successors. And we reach node J and K. I was going in the wrong direction. And then J does not have successors, so we back up and we pursue node K, and we go on through F, expand its successors, reach node L and M, and then we look at L. L has no successors. We back up and we pursue then M, which is currently deepest, and we continue on in that fashion. And so what you find in your implementation of depth first search, it uses a stack. It's the same search algorithm as breadth first search. I always have to pause when I say that, of breadth first search, where breadth first search uses a queue. It's the same algorithm, the same pseudocode, just a different semantics on the frontier queue that you employ, right? So it's literally the same thing. And it's kind of beautiful, right? And you get an entirely different behavior and different set of performance characteristics, also different pathologies, just by changing the selection criteria about which nodes you choose by changing that data structure that implements your frontier. Okay. Excuse me. Any questions? No? All right. Now, there are some treatments you could absolutely implement DFS and BFS using recursion. I prefer, it's just an opinion, using iteration instead of recursion because there are more opportunities to make use of interesting data structures and memory storage versus relying on automatic storage, i.e., your call stack. Okay. All right. Any questions? No? All right. Excuse me. But DFS is not cost optimal. It's not always going to find the cheapest path from initial node route to goal. It returns the first encountered solution, the one that's deepest or preferring deepest paths first, not necessarily the cheapest path. Um, for finite tree or organized spaces, it is complete. If there is a single solution, it will find it, but that doesn't generalize to things that are not tree-based spaces, spaces that are naturally organized as trees. like your 8 puzzle. And so if you have an acyclic state space, DFS can still have different expansions of the same state. It can pursue in depth, okay, I visit a state, I visit that state again. And so DFS is not known generally to be optimal. Um, in a cyclic space, it can get stuck in infinite loops because it doesn't know I should stop. So you need to cycle check. And as you visit nodes, when you put them on the frontier, one of the pieces of information you can add, in addition to the action that you use to arrive to that state and the path cost, you can also decorate that data structure with the parent pointer. And it's through that parent pointer you can reference from a node to its parent, to its parent, to its parent in pursuit of checking whether or not, for some number of generations going into the past, whether or not you see yourself, your identifier as a node that occurs, right? So that's your cycle check. And so if you have an infinite state space, depth first search can get stuck in an infinite path, right? It's not complete. It'll just keep going and going and going. So you have to be careful with depth first search. But the good news, well, it has a smaller memory complexity, which is always good, especially as you scale to much larger problems, more complex state spaces, which is in contrast to breadth first search, which has an exponential complexity on storage as you expand your frontier. Right. Any questions? No questions? No? And so let's take a look at sort of a pathological case or typical case of depth first search. You're pursuing down the tree, and let's imagine you have some parameter m, which is the maximum depth you're going to pursue for a finite space. And let's imagine a branching factor of b, and certainly in the book and in my slides, because I like to reflect the book, we display binary trees just because it's easy to explain. But you can have an arbitrary branching factor, and your tree, your time complexity for depth first search, because you visit a node and then the next deepest node and then the next deepest node, the execution time, which is the number of nodes you visit or nodes you consider, you could say it that way, is going to be proportional to the number of vertices or nodes you have in your state space. Now, certainly if your state space is really large, in practical terms, you can't always search exhaustively. But the memory burden is this branching factor times the max depth. And if you think about what happens at each depth, you expand the frontier, you get the child nodes, that's your branching factor B, but then you go down as far as the maximum depth M. So you can imagine this rectangle I have on the inset sort of slid over some part of the tree. Let me see if I can get this running. I don't know why it's not working. There it is. You can imagine this rectangle. If you have this depth, there's your B, and here's your M. Okay? So that's nice, and that's a lot better than we saw with breadth first search, which was B to the D, right? Anything exponential is not tractable. All right. Any questions? No? Makes sense. And so one of the ways you can almost use the benefits of the memory sparsity of depth first search, but also try, with an emphasis on try, to get some minimum path qualities of breadth first search is by limiting your depth first search to some depth threshold we'll call L. And so essentially what you do is you probe your search tree. You set your depth limit to L, and you start out with a depth of 0, do your DFS. Then you increase that to 1, to 2, to 3 each time, doing depth first search, limiting how deep this search is going to proceed. And if you think about what breadth first search is doing, breadth first search says, I'm going to expand my frontier, limiting to all those nodes of depth D minus one. And it's only once I exhaust all of those at depth D minus one do I proceed to depth D. In essence, what you're doing with this depth limiting modification to depth first search is you're saying, I want that benefit of BM memory burden, and I don't want you to exhaustively do the search because it's going to take a long time and not give me the optimal solution. So I'm going to limit you so that you're only going to go to depth L, depth 0, depth 1, depth 2. And once you're done with that depth, only then will I allow you to pursue something deeper. So in essence, it's kind of almost doing what breadth first search is doing, considering depth D minus 1, then depth D, then depth D plus 1. Only with this, you get the benefit of this memory sparsity that depth first search affords you. Does that make sense? And so with all of these algorithms, there are a lot of little tweaks and tinkers and changes to components that you can apply and get some nice desirable properties. And we'll see an interesting take on that when we do take a look at bidirectional search. Okay? All right. Any questions? No? And again, my paranoia about my headset not cutting out. No, it's there. Okay. So here is the algorithm. It's called Iterative Deepening Search. And as a module you call method is depth limited search, which is effectively depth first search. But the difference is you're evaluating the depth of a node after your goal check to see if that depth has exceeded the cutoff. And if so, you say stop and you return, and then you iterate in the iterative deepening call with that next depth over which to proceed. Does that make sense? But for every feature, there's a cost. And iterative deepening or this depth limited search has to pay a cost. And what that cost is that if you're going to probe at depth 1, I won't say 0, 0 is the root, and then you increment to depth 2, well, it revisits everything pursuing depth 2 that it visited at depth 1. So that means the nodes that are earlier or closer to the root are going to be visited multiple times. And the nodes that are closer to the leaves of the expansion of the tree are going to be visited, ultimately leaves only one time. But thinking about the structure of a tree-based graph, there are more nodes towards the leaves than there are towards the root. And that means you spend less time evaluating the majority of those nodes that are in your search tree. Does that make sense? All right, because it's multiplicative as you expand down. And so what this is cycle is, it's another routine inside of depth limited search. It says, okay, well, I'm going to check a few hops up the parent chain to see if I reoccur because I know my node ID. I have my parent pointer because that was from the node that I expanded. So I just chase that a few times, referencing that and referencing to see if I reoccur. Now, you don't always have the opportunity to do a cycle check all the way back to the root, but typically cycles don't occur at the full diameter of the graph. So you only need to go a few steps and you pay the cost of big O of 1 for 3 hops per cycle check or 4 hops or 5 hops. Right, any questions? That makes sense? All right. And so when you have a map, and we refer back to the Romania problem, we have a total of 20 cities. And if you start in one of them, that means you have 19 other cities that you can visit, 19 other states. So you could think, gosh, well, if I limited my depth to 19, then I can ensure I can visit all the nodes. But if we pay attention to the diameter of the graph, the effective depth, you can reach any node from any other node in 9 hops or in 9 edge traversals. And so this depth limited or iterative deepening search saves you because ultimately you rarely want to pursue the entire diameter of the graph. You can do your search and get those benefits of coverage that BFS gives you, but the memory sparsity that DFS gives you. Does that make sense? Any questions? No, no questions? And so it has the benefits. The time complexity when you have a solution is big O of B to the D, okay? And it's big O of B to the M, the max depth, when there's no solution. Because when there's no solution, ultimately, you're going to have to pursue everything up to that max depth on these subsequent calls to DFS. Space complexity is big O of BD when there is a solution, and big O of BM when there's no solution. But that still beats big O of B to the D power, right? It's not exponential. And so you can mix and match and tweak and tinker some of these algorithms and combine things to get some interesting time and space complexity benefits. Okay. Any questions? No? Okay. So here's an illustration. This is in the book. I forget the figure number of iterative deepening search. And so we start out, and this is a tree-based search. So you notice here, the grayed out nodes are just to show you where it's going. But this kind of looks more like what the agent's perspective, the so-called egocentric view, looks like. So we start out with a depth of 0, and it's trivial. We are at the root node. We stop, and then we iterate our depth limit L, and we pursue the left child and the right child at that depth of 1. So then we stop because we hit that depth limit, and then we increment, and then we pursue again at depth 2. And you notice that node B was visited during our depth limit of 2 as well as our depth limit of 1. And so as we proceed, we can walk down the tree, but in this case, we're considering we're limit of 1, all of those children at the first depth, limit of 2, all of those children at the second depth, limited to 3, we visit those nodes or encounter those nodes at the third depth. And so it kind of looks like breadth first search, but you don't pay the cost of that space complexity that breadth first search incurs. Okay. Any questions? No? All right. Okay. Why is this frozen? Ooh, that's not supposed to happen. Yeah, sure. Uh, because you can't do backups. Um, if you maintain the leaves from the previous iteration, DFS is a stack, right? And so you're always going to pursue that last one. You're continuing on and you're not starting from the root again. And so the definition, I mean, you could try that as an optimization, but you're going to have some problems because if you want to construct the backwards path as you expand the frontier, you're going to well, first of all, you pop nodes off the frontier, right? So then one of the questions is how do you preserve all those leaf nodes from the previous depth if you have popped them off? So then that means you have to maintain some side list that memorizes it. And then once you're done memorizing it, you then present it back. But then you never gave it an opportunity to construct that path from the parent because each time you set the depth limit, it's a different call to depth first search. So then that means you also have to share FIFO queues between different instantiations of depth first search. So could you tinker with an optimization? Absolutely. Anything's possible. But it's not always recommended you do that, but I'm sure somebody somewhere is doing some information sharing of that sort with various data structures, right? Did I answer your question? Um, Let me go back to share. I don't know what happened to my fonts when I switched the slide. Um, so hopefully it doesn't do that when I restart it. Probably had to do with the sketch pad. There it is. So let me see what the next one. That's not good. That's not good. All right. So as I said, when I did work for the Army, embrace the suck, right? I don't know why I did this. This is not what it's supposed to be. And so I apologize for this. You invest a lot of time in making slides and things don't display like you just saw them last night. Um, so IDA star, it starts near the root and it's evaluated many times. There are more states in the tree count-wise towards the bottom because the nodes are exponential with the depth and it's exponential in the depth based on the branching factor. So there's more states on the bottom, and you're visiting fewer states multiple times. And that's where a lot of your savings come from. So then if you look at the number of nodes you visit, it's on order B to the D. And where that comes from, it's dominated by the number of states that are towards the bottom of the tree, the leaf nodes, right? But you D many times if your threshold is that depth D for your depth limit. D many times you're going to visit nodes at the first level. D minus one many times you're going to visit the second level, and so forth. But this sum is dominated by the leaves, and therefore our asymptotic is big O of B to the D power. Okay. All right. Again, I apologize for these. This is a big surprise to me. But so IDA, oh, it's a repetition. Oh, that's weird. And the picture went away. Go figure. All right. And so another take on this is so-called bidirectional search. And as the name connotes, you have a search from the initial state, in this case for a Romanian vacation Arad, and it proceeds forward toward the goals. Concurrently, you pose the same problem in the opposite direction. You formulate that problem as starting in the goal states and working your way in the other direction, the backwards direction, towards the initial state. So in that case, your goals become your initial, and your initial state becomes your goal. And so you have two frontiers, one in what we'll call the forward direction and one in what we call the reverse direction. And there are two different depth searches going on at the same time. So then how you determine whether or not you get a solution is whether the forward frontier and the backwards frontier, as they pursue nodes, whether they collide, they intersect with one another. And so you can put in that check to say, is this node in my other direction search? And the benefit of that, first, any questions? No? All right. The benefit of that is your complexity is saved. Rather than big O of B to the D, it's big O of B to the D upon 2, right? So in that case, you're dramatically multiplicatively reducing the complexity. But of course, the cost you pay is in a more complex implementation. Okay. All right. Any questions? Yes, Nikki. How do you ensure that the goal doesn't go to the, I'm sorry. Hmm. Hmm. I see. I see. Thank you for your question. And so literally, when you start the search, instead of initializing it to the starting node, in this case, Arad, you would literally set your init state to Bucharest because the edges don't have a directionality associated with them, right? When we proceed with search, our idea of successor are just going to be those nodes that we can reach through one hop. And certainly your transition table would be different. You're just going to reverse which is the starting node, which is the landing node in your transition model. And so literally, um, it looks just like any other tree-based search in terms of the implementation, only some things change, namely what the goal state is, what the initial state is in your transition model. Because if you say, what's my next state of Bucharest, it has to be Patesi and Figueras in this example. If you said in the reverse direction, if you said, what is the successor of Arad, right? That transition model is what recommends or refers to you or gives you what that next state would be through an action. And so it's still the same actions. Well, it's still a set of actions, but the transition model is going to change when you have the forward direction versus the reverse direction versus the forward direction. Okay, but it's no different from doing any kind of depth first search. You have your initial node, you have your transition model, you have your path cost, and it's just a matter of what direction that model is driving your successor in your exploration of the frontier. Okay. All right. Any other questions? No? All right. So you can get this savings. And the idea then, and this refers to that, you get a collision if the successor of the forward direction for state S is S prime, and at the same time, the successor of S prime in the reverse direction is S. And so you return your solution on collision, but then you have to stitch together those partial paths that go to that colliding node in the backwards direction and the forward direction. And that's pretty straightforward to do. Okay. All right. Any questions? No? Make sense? All right. And so this is some pseudocode. This is from the book, and it's a bi-directional best first search, right? These acronyms get pretty interesting. And so with this, you have two problem formulations. You have problem underscore F or lowercase f, that's the forward problem, and you have problem subscript B, that's the backwards problem. And so in your problem description, you have a starting state, you have a transition model. The two would be different based on what direction it's presumed that you're traveling. And then you have an evaluation function. Recall best first search was kind of like minimizing the gradient of some function. The function that returns the path cost for the forward direction would be a different implementation for a function that returns the path cost for the reverse direction. So you start out and you create your initial node. In the case of the forward direction, your initial node is Arad. In the case of the reverse direction, your initial node is Bucharest for the Romanian problem. And now I've given you the map, and that map kind of deceives you. All they are nodes, right? And you can set any node you want in a graph as your initial node and any node or nodes you want as your goal nodes. Because at the end of the day, remember, your tree is derived from your state space, and your state space takes form often as a graph. And so the transition model is part of your problem description as well. And you'll note here, you create two priority queues, and those two priority queues are ordered based on their respective evaluation functions. And then you initialize your frontier in the forward direction with initial state for the forward direction, in this case, Arad for the Romanian vacation example. And Bucharest is the initialization of the frontier for the backwards direction for that particular frontier. Okay. Any questions? No? Make sense? Yeah. All right. And so, of course, you can have your reached, and your reached data structures are going to be different for the forward direction versus the reverse direction. It's only once you're generating successors that you want to check to see if you have a collision. So you can kind of keep those two separate, run them, and then check to see if there's a common state that you both arrive onto. And so as long as you're not terminated, you're going to look at the top node on the forward direction frontier and the reverse direction. And so what it's doing here is it's saying, okay, well, what is my next best node to pursue, to expand? And that could be some node that's in the frontier for the forward direction. Conversely, it could also be some node that's in the frontier of the reverse direction. So then we go ahead and we do this proceed, and this proceed is where we actually pop off of the frontier, given that particular problem. And so once we call proceed, it kind of doesn't matter which problem we're looking at, evaluating or generating or expanding nodes for, whether it's the forward problem or the reverse problem. You expand the node, and then we check the path cost, and then we mark the reached data structure to say we visited that child, and it's different if it's the forward problem or the reverse problem. And then we add it to the frontier, and then we check to see if that newly encountered node is in the other, I won't say to forward or backwards, is in the other problem reached data structure. And so when you call this, you'll notice here in the pseudocode, it'll say reached and reached to. When we call proceed in the Bi-BF search routine, the first invocation to proceed, we have the forward problem reached, the forward problem, let's see, reached. Uh, the reached data structure for the forward problem comes first, and reached to is reached for the backwards problem, and we reverse those roles when we're looking at the backwards direction for proceed. Does that make sense? And so the only linkage between the two is this collision detection. And we reverse if we're executing expansion for the forward problem, we say, did this newly encountered node collide with the backwards? And if we're expanding for the backwards problem, we say, does this newly encountered node collide with the forward problem? Does that make sense? All right. So this would be a cool, well, we won't be doing this for this class. Would it be a fun thing to try if you're interested after the class or what have you? All right. Any questions? Does that make sense? Yeah. All right. So um, that's all I had. So we'll continue on with the code. It's a good time. We have about 35 minutes. Okay. All right. So I'm going to bring up PyCharm, and I'm going to bring up the code. The code is on the Canvas side. It's the same code that you tinkered with before. Um, I don't want that one. Okay. So the zip file is CSCI 210310 project 2 code. So I'm going to bring up PyCharm and do a little walkthrough, pointing out uh, some important points. I want to make sure I bring up the right one. I don't want to show you the solutions. Um, Open. Let's see, it's going to make me traverse all the way up. AI, projects, project 2. And we had this one, project code, open, this window. There we go. Okay, I'm in the right place. So your implementation is going to be limited to code you modify in two places as I let this index. One is in search.py. Please be empty. All right, yes. And the other is in search agents.py. And so what I'm going to do is walk you through a few important points. And the first order of business has to do with the data structures that you use. We talked about depth first search using a stack, and we talked about breadth first search using a queue, and we talked about best first search using priorities. And so when you use these data structures for queues and stacks and so forth, you should be using those data structures out of the util.py code, right? So you're going to import util, and from util, import stack, priority queue, and queue from here. And the reason for that is that there's instrumentation in there that's used by the autograder, right? So it's really important you use those data structures that are provided to you with the example code, okay? All right. The other thing inside of search is where all of your implementations for project 2 are going to reside. And you'll see here an empty method or a method stub, so to speak, for breadth first search. There's one for depth first search. and there's one for uniform cost search. There are heuristics for A-star search, and so forth, right? It's outlined in the PDF where you can implement what, as well as running it. And so here, the search problem, let me bring up, tell you what, let me set a breakpoint here. And then I'm going to bring up my run with parameters. Uh, Let me do one thing because I can't remember. There we go. All right. Okay, I remember. Tiny Maze search agent. All right, let me go back in here. Tiny Maze search agent. Okay, so let me apply. Um, and let me close and let me debug. All right, so let me go into pacman.py. And I recommend that you get used to stepping through the code, driving around, so to speak, in the debugger. It's a really good exercise to see how things fit together. No, I don't want Proj2. Let me change the interpreter directory. To code Proj2. Why is that? There we go. Okay, oops. Let me, nope. Let me pick my Python environment. I have it set up where I switch between home and here using stuff staged in Dropbox. So I have to, oh, come on. No, DSC 125. Why is that doing that? All right, so let me run with parameters, project default, project 2, virtual environment, run. See, that should. Okay, all right. Let me go back to the debugger and let me, there we go. All right, good. So I'm going to step in. Let me just continue, see if I can hit the breakpoint for, nope, the wrong one. Oh, nuts. Let me go to the PDF. Project 2. Um, Search, get the command line. Some intro. There we go. -L tiny maze search, and the default is depth first search. Okay. All right. Let me, oh shoot, I'm not recording the screen, am I? No, I'm not. Oh, that's a good thing then, I guess. Share. All right, there we go. So this will end up on video. So let's go ahead and we're going to edit this configuration, and I'm going to give it the parameters needed to run -L tiny maze, -L tiny maze, -P search agent. Oops. -P search agent. And then we will give it tiny maze search, which is -A, the search function. -A fn equals tiny maze search. Okay, let me make sure I got that right. Okay, so when we do that, oh, come on. All right. In the interest of time, let me just walk through the code. All right. So one of the things that you want to make sure you pay attention to is inside of your depth first search routine. There's some example code to print out various pieces of information. You want to be careful when you call on the search problem, get successor. Get successor, absolutely. It looks at all of the admissible actions for the state that you call it on, and it will look at those child states. But one of the issues is that the search problem records that move, right? And so one of the confounding things when I was going through the solution is that if you just are curious what that state is, you call get successor, and then you go ahead and you engage in your depth first search, which towards the pseudocode is in the slides and in the book, um, you're going to see that initial node appear twice, right? In your solution when AutoGrader exercises it. And so you don't want to call get successor on any state unless you want it to register the state that it visits, right? That it expands. Because that instrumentation inside of the search problem is used by the autograder to record the sequence of states that you visit, and it exercises that with the test cases in order to score your assignment. So if you were having a command like this to, in the debugger, view what's going on and how things look, you want to comment that out. It's a pretty confounding error, right? Um, any questions? No? And so never call get successor unless you actually want to get successor. And if you're testing out, one of the first things you should do is instrument with this code, with some gets and some printouts and stuff like that. And so the first thing you're going to do is you're going to bring up your depth first search algorithm. And of course, there's no depth first search. There's a breadth first search, but breadth first search and depth first search are one and of the same. And so the first thing you're going to do is you're going to get your start state. And your start state, um, there's a method for that in the search problem. If we look at the search problem class, and I'm not going to do that in the interest of time, it's a lot easier to drive through the code in the debugger. And one of the things you can do if you right click, you can go to the declaration and the implementation of various things. It's a lot easier to do. If you're in a modern IDE environment, use those features to help you navigate where you are. So you start out and you get your start state, and your start state is accessible through the search problem method that's given to you when you call depth first search. So then the first thing you do is you check if it's a goal state, right? And there's a method for that. It's goal state, and that's going to return a Boolean. So literally, it's just like the pseudocode. And then after that, you're going to create a FIFO queue or a stack, making sure you're using that implementation of stack that's in your util.py. Now, util.py, you shouldn't be modifying anything. The only place that you're going to be applying implementations is in search.py and search agents.py, keeping in mind that you never modify method signatures for those methods that are given to you. You're going to add implementations. You're welcome to add new methods. You're welcome to implement within a method, but please don't change the method signatures for the code that's given to you, or you'll break the autograder. Again, there are many opportunities to break the autograder. Automated testing for something like this is a pretty non-trivial task. But nonetheless, using the stack, the first thing you do is you push your initial state onto the frontier, right? And you'll notice here, you never expand nodes without taking them off the frontier. And it's the frontier selection criteria for nodes that are placed on it that tells you or guides the progress or the type of the search. And so you start out, and as long as you have nodes that you can expand, you're checking to see if that stack is empty, you go ahead and you pop off that element, the first element, and then you go ahead and you expand the node. So when you expand the node, that's when it looks into, you call get successor on the search problem, and it looks at the admissible actions, looks at the transition model, and it returns back to you an iterable that contains all of the successor nodes. So for each one, okay, you go ahead and you check, is this thing that I expanded the goal state? That's when you do your goal check. If so, then you return it. But in this case, when you return it, you're going to return a data structure, right? And this data structure is going to be a list of all of the actions that were executed to get to that particular child node. So every time you push something on the frontier, you're not just pushing the node. That's one of the things. You're going to have some kind of data structure, leave it up to you, that's going to store a couple pieces of information. One is the state. One is the list of actions to get to that state. And one is the path cost to get to that state. And you can build those things incrementally. Now, of course, when you expand the initial node, right, each time you create a child, you know when you did get successors, it'll give you the child node, it'll give you the action to get to that child node, and it'll give you the step cost. And so using those pieces of information, you can construct the set of actions that got you to that node. For the root, it's just going to be an array of one action. But if you were to pop off a first depth node, it's going to have a list when you expand successors, and you're going to append that action for its successors to the list of actions that you got off the frontier for its parent. Does that make sense? So everything you need on the frontier, it's not just the node. You need other pieces of information. Okay? All right. Any questions? No? And so once you have your implementation of depth first search, it's just a change of a data structure for the frontier to implement breadth first search. And one of the things you find when these two run, one of the things the environment will report to you is the number of nodes it expands or it encounters. And you'll find that it's much bigger for breadth first search. Okay. All right. Consistent with the asymptotic behavior. Okay. Any questions? No? So the key takeaway, and I wish I could fix this issue, but the key takeaway is to make sure you're using the data structures provided to you in util.py. Without those data structures, you're not going to get the instrumentation that the autograder relies on. Right? That's really, really important. And then the other thing is to basically translate the pseudocode to Python code, and you're going to be using iteration to do it. And at the end of the day, once you reach the goal state, it's going to return back that list of actions associated with the goal state that you constructed when you popped off the frontier and did the generate successors. Okay? All right. Any questions? No questions? And so the first one you do will kind of take a little bit of time, not a lot of time, making sure you stay faithful to the pseudocode and also making sure of what you're putting on the frontier. It's not just a node, right? It's a data structure of a couple of things. Okay? All right. And so please, make sure you jump on it early. Feel free to discuss, debate, argue with your colleagues in the class. And if you have questions, don't hesitate to post on the course Slack channel. And you should be able to get done the first three searches because they're just variations of one another. Once you've implemented depth first search, you already have breadth first search and best first search. They're just minor tweaks on one another with data structures and mostly the FIFO data structure. Okay? All right. Any questions? Yes. Elliot, yes. Mm-hmm. I would focus on driving through the debugger, but in specifically when you call get successors, it's going to return a couple pieces of information to you. It's going to, mhm, yes, they're directions, yes. And so ultimately, when you encounter a goal, you're going to return back a list, and that list is going to contain all of the direction moves that your Pac-Man took to get from the initial state, initial position, to the goal. And when you look in the debugger as you're developing, I strongly encourage everybody to drive through it. Um, the state itself is the XY coordinate of the Pac-Man in the environment, right? And the action is one of those directions, north, south, east, west. And so you're going to be constructing and returning a complete list because this is a planning algorithm. And in that planning algorithm, when it halts, what it returns is a complete list of all of the actions in sequence that you took to get from that path to the initial state, in this case, which is the initial position of the Pac-Man, to that goal state, which is the goal position of that Pac-Man. And so, to answer your question, that's a great question. Thank you for asking. You're going to be returning a list of directions or actions. And in the environment, when if you look at the Pac-Man .py and you look at, I think it's yeah, Pacman.py, it underneath the covers converts that direction to a vector, and that vector will either increment or decrement the y component or the x component, so that when it renders the Pac-Man on the next turn, it'll update it. But that's not important for this class. What's important is that you're going to get back your state, and your state is this xy coordinate. But it's not just the state, it's the state, the list of actions that got you to that state, and the path costs. Okay. And so when you call depth first search, breadth first search, best first search, what you're returning, because you're iterating through all of these popping off the frontier, encountering nodes, expanding nodes, what you're going to be building ultimately, when it returns, it's going to return back to the Pac-Man environment, a complete list, which is the solution to get from the starting state to the goal state, right? That's different from other types of Pac-Man agents. But the assumption is this computes a complete plan and then returns to the environment. And then the environment in the game loop, it takes this array and then it walks through each one of those actions from your plan and then goes ahead and updates the display appropriately. Okay. Any other questions? No? All right. And so key consideration is the data structure. Make sure you use what's in util.py. And also, when you're putting nodes on the frontier, the pseudocode says put a node on the frontier, but it's not just a node, right? It's some other data structure that's going to contain a couple pieces of information. All right. Okay. Any questions? No? Again, oh, yes, Colton. Ah, yes. 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 Now, inside of get successors, in the search problem, go to implementation. Oh, where'd it go? Oh, come on. Are you not going to do it? I think I clicked the wrong thing. Go to implementation, get successors. That's a position search problem. All right. So we call get successors, and it converts the direction, which is north, south, east, west, to a vector, and that vector will either increment or decrement. But one of the problems here is this condition, right? It'll say, have you visited this state? And it goes ahead and it appends that state. And so it builds a trace of all the states the Pac-Man visits. So that call to get successors is maintaining, in this case, um, the initial node. So then, if you decided in your while loop put it on the frontier, and then pop it off, and then expanded it in through get successors. In this registration, this history of states expanded, it's going to have your initial node from when you first called get successors, and then your initial node again from that first time in the loop where you popped and called get successors. And what ends up happening in the auto grader, um, it has some example graphs that it tests your implement solution against. Instead of saying if it should be A, B, and C, it's going to have recorded for you A, B, and C, and it's going to fail. And so if you are calling for debugging purposes or, just to, drive around the code and test, never call get successors unless you actually mean it algorithmically. Well, I shouldn't say never. You just comment it out, right? That's going to confound what the auto grader understands is the sequence of nodes that you've expanded through the execution of your search algorithm. Okay? It's really, really important. It's not documented. It bit me in the butt. I spent more time than I care to admit learning that. So I hope that saves you the burning time unnecessarily. Okay? All right. Any other questions? No? All right. So it's 1:05. If you have any other questions between now and Tuesday, I'll figure out what happened to my environment. I think I know what happened. I have a setup at home on a Mac desktop, and I do everything in Dropbox pointing to the same bits. And so my environment from home, which is slightly different from my laptop here, um, for some reason, it's not changing it. So I'll figure that out. But if there are no other questions, we can end there. Good luck. Please don't hesitate to reach out if you have questions, and feel free to discuss the concepts, to debate, to argue, discuss with your colleagues in the class. I want to make sure you really understand this first one because the first one sort of keys you in on everything else. Okay? All right. Thank you. I'll see you all on Tuesday.